Welcome back. I want to continue my discussion today on EM algorithm. In particular, I want to give a classic example for the EM algorithm, the basically parameter estimation for a Gaussian mixture model. So my Gaussian mixture model is something like that. I have, for example, a mixture of 3 Gaussian here. So basically, each sample can be drawn from one of these Gaussian with certain probability. And then therefore, like the given, let me write x as the sample and theta as the parameter as last time. Then this conditional probability can be written as sum of the pz x given theta. Z here is the latent variable. In this case, is just representing which distribution that the sample is drawing from. So therefore, k is equal to 3 in this case. I have 3 different clusters, 3 different distributions in this example here. And then I can expand this pc x given theta as pc given theta and pz given theta. And the first term here is just a pi probability that what's the probability that a sample is drawing from one of the distribution. In particular, alpha k is the pi probability of drawing from the k distribution. And the second term is nothing but just a Gaussian distribution with the corresponding parameter mu k and sigma k. Here mu k is the mean and sigma k is the covariance matrix. And of course, this can be written in this form here. Here I allow a more general case that x is multivariate Gaussian, so it's a vector case here. So I therefore xk, sigma k here is a covariance matrix. Then okay, this is our model, basically the Gaussian mixture model. Now to do the EM algorithm, let's start with the E step. I want to update Q at the t+1 iteration as pz given x theta t, and I just rewritten the equation here, and this pz given x theta t can be written as this form here using base rule, and the denominator here I can be written as this guy here. Basically can be think of a marginalization of this joint probability here. Actually, you can see this expression is the same as above, as the numerator, and this conditional joint probability can be expanded using base rule again as pz equal to k given theta times px given z and theta, and note that this is nothing but this expression here, this term here. So this is really alpha k, the pi probability that a sample is drawing from the k distribution, and this second term here is nothing, just the Gaussian distribution. So therefore this is our E step. It's a very simple expression here. Okay, let's continue with the M step here. For the M step, know that like for E step there I can like compute the update like one sample at a time. Basically the Q step, E step update is trying to find the membership of each sample, but for the M step is trying to find the to maximize the objective functions such that the parameter is optimized. So in that case, we need to scan for all the sample at one time. So I really should have written here, like when we derive the the EM algorithm, the M step, we kind of only looking at like x, just as if we only have one sample here. But instead, we really should look at more than one samples. So when we have many samples, basically the expression should be the same, because we can think of this z and x is just vector variables here. So then let's say if we have two samples, then we'll just have like x1, x2, z1, z2 here, and we're supposed to sum over z1 and z2. And know that like given theta, this x1, z1 and x2, z2 should be conditional independence. So therefore I can split them into like this. And then I just regroup the term here like this one. And since this term here does not depend on z2, so I can really sum over z2 here, so I get this marginal probability without z2 here. So if z1 only, this is also like with z. Similarly for the second term, I have this q here only with respect to z2. So for generally, if we have m sample, basically we have this, we will have n samples, we will have n terms here, n of these terms here of summation over z. Here I use sum over k instead, like k is the values of z. And I basically have this log x n zn equal to k given theta, and this q qt plus 1 n is kind of shorthand notation for this qt plus 1 zn given x1 and so on and so forth. x1, x2 and up to 6n. Okay. So now we are ready to derive the m step here. So we are trying to maximize this subjected to theta. So we call what is theta exactly? The model we have is really a Gaussian mixture model. So Px given theta is like this, sum over Px z given theta here. C is the latent variable, and we have this pi multiplied by this probability. This one is this Gaussian kernel here. So therefore you can see the parameter really is alpha, mu, and sigma here. So I can write the objective function as this, and I add this term because I have extra constraint on alpha. Alpha is a PMF here, so it should be summed up to 1. So I add this Lagrange multiplier, just take care of this constraint. Lagrange multiplier term to take care of this constraint. And of course there are other constraints, but it turns out that we can ignore it for the moment, and it doesn't affect the result. Therefore I don't add other Lagrange multiplier. For example, for sigma k is supposed to be positive definite, but we can ignore the constraint for the moment, and it doesn't affect the result. But this one we have to add this, otherwise the result won't be correct. So anyway, then basically we can find the maximum of this objective function. Now we have this objective function with respect to theta, so we just take the partial derivative to 0. So let's try to take the partial derivative with respect to mu k first. So let me write down this objective function. Okay, write down the f first. F is equal to as we showed earlier, is a sum over n and sum over k, that with this whole thing here, that this is q, t here, this is the kind of membership probability that we obtain in the E step. And this log p c given theta can be expanded into log alpha k minus this thing here. Is we get this out is basically from earlier on the Gaussian PDF here. Basically, we're taking the log of the Gaussian PDF, and therefore we got those terms here. And then let's say if we try to take the partial derivative of this L with respect to mu k here, okay, the second term here does not depend on mu k, so it will become 0. So we only need to care about the partial derivative of f with respect to mu k. And the only term they have mu k here is the third term here. So this the first and second term doesn't have mu k. So therefore the only terms you have is taking partial derivative of this with respect to mu k. This gives us this term here, that this we use a this simple matrix derivative results, that the partial derivative of xt x transpose ax with respect to x is equal to a plus a transpose x. It should be pretty easy to verify actually. And then we can revise this since this sigma k is symmetric. So sigma k inverse is also symmetric. Sigma k inverse transpose is equivalent to sigma k inverse. And therefore we just pull out this sigma k inverse here, this 1/2 each, and then we'll pull out this here. And that's it. And this thing should be equal to 0. I'm missing this. This should be equal to 0. And then therefore, like, we have this here. So this is the update for the mean mu k. Okay, let's continue to look at how to update sigma k. Let's see. So for sigma k, again, I should try to optimize the objective function. Now it's L here, subjected to L here with respect to sigma k. So I just take the partial derivative of this thing, whole thing over sigma k, but whole thing with sigma k, but the second term doesn't have anything to do with sigma k. So only the first terms have things with sigma k, basically this term of sigma k, this term of sigma k. So if I take this term with respect to sigma k, I can kind of expand this log determinant. Is basically I can write as log. This is a constant 2 pi to the power m. Assuming that the covariance matrix is m by m. Anyway, this is just a constant, so this is just 0. We can ignore that. We only have the second term here, partial derivative of log determinant sigma k with respect to sigma k inverse. So we want to take derivative of a sigma k inverse instead of sigma k, just for the reason that like we are able to get a nice solution if we do it this way. So anyway, so this second term here, I can change this sigma k to sigma k inverse if I just flip the sign here to minus. And because I basically the determinant of A is equal to 1 over determinant A inverse. So therefore, if I have a log there, it will just flip the sign. So in any case, this expression actually turns out very nice. It's just equal to sigma k transpose. And this is basically using a matrix calculus result. This one, partial log A inverse over partial A inverse is equal to A transpose. One can verify it quite easily without too much problem. And then for this term here, so similarly, if I take the partial derivative with respect to sigma k inverse, I will basically just get this one. Again, we use some matrix calculus results that is partial derivative x transpose ax with respect to A is just xx transpose. So with these two values here, then like partial derivative of L with respect to sigma k inverse is just equal to this. And if I set this to 0, basically the sigma k update will be just equal to this expression here. So I just shuffle the term. Basically, this term here, if I consider this first term here, if I move the second term here to the other side, I have this here. And this, of course, is independent of this n here. So therefore, I can put it out, and sum over this q will just give me this expression here. So therefore, that's what we have. Okay, let's look at the updates for alpha k now. So again, we should just try to take the partial derivative of L with respect to alpha k, and this will give us this term here. So unlike last two cases, basically the last term will depend on alpha k also. So therefore, taking derivative of this last term will just give us minus lambda. And taking partial derivative of f with respect to alpha k will just give us 1 over alpha k multiplied by this term here. And we should set it to 0. And if we set it to 0, we get alpha k is basically just equal to this. This is just taking the qn from the e step and sum over that over lambda. And but what's lambda? We can find lambda by trying to normalize alpha k, because alpha k is a PMF here. It should sum up to 1. So therefore, if I try to sum up alpha k, I will have this one set to 1. I can flip the summation here of sum over n and sum over k. If I try to sum over k here, this is just summing over all possibility of z here. So this is just give us 1 here. So therefore, like, I am basically summing 1 for n times, so therefore I should just have n here. So n over lambda is equal to 1, therefore lambda is equal to n. So therefore, like, alpha k is basically just the correct update should be just like this. Okay, let me try to summarize here. Basically, we have these steps as shown here. Is trying to find for each data point xn the corresponding membership or the distribution of membership of this data point, whether it belongs to any particular distribution k. And after finding this, okay, based on this expression here, So after finding this Q here, we'll just use this Q to update alpha, mu, and sigma respectively. And as you see, like for mu and sigma here, it's nothing but it's really computing an empirical weighted mean and average. So weighted mean and covariance. So this is just a covariance approximation. For example, is weighted by this Q here. That's the distribution of a data point belong to any particular distribution K. So after we update alpha, mu, and sigma, we'll just go back to the E step and continue to iterate like this, back and forth. So let me just show an example of how this actually works in practice. So I already have written a MATLAB code and have like 3 distribution, basically, which I have a mixture, Gaussian mixture model with three distributions here, and it's approximately, you can see that these 3 clusters here, and this is the initial mean estimate, so arbitrary pick here, and you can see that as I iterate, let's see if I now for example, each time I iterate here, it's getting a little bit better and better, and the color here basically also show like what is the data point, or for each data point what is the corresponding, whether it's belong to a red cluster or a green cluster or the blue cluster. I mean the boundary you can see like it's not very certain, it should be red or green and so on. So so in the E step, basically for each of these data points is trying to figure out whether it belongs to each of the cluster. So you can see like for data points like this, they are very certain to belong to the red cluster, but like here, it's not sure whether it belong to red or green. So, but approximately this is the kind of the domain of the, or like the neighborhood of or like all the data points of the red cluster, and belong to the red cluster, and but in the M step we're just trying to find the empirical mean and covariance for that. So it's basically just find the weighted mean is approximately here. So as we, of course, after we find this mean, then we're trying to, after we update the mean, we're trying to readjust the membership of each of these data point here. So as the mean move to more here, so data point in this boundary here become more, in the past maybe it's belong to the, we are not certain it should be green or red, but as you see that if we move here, this become more and more green. And of course, like, because it's more green now the kind of like the number of data points belong to this one is shrink, and the corresponding mean now of this data point also moved, as you can see like now, the red move more and more to here now, to the left. And as we continue, let's just continue to iterate. And this red here more or less converge, green converge, blue also is converging very slowly. I guess it's more or less stable now. Actually, this converge pretty well to the actual means here. The actual means that I pick is 0, 0, 0, 7, and 4, 0. So it's more or less converge to the actual mean. So basically that's all I want to talk about. And last thing I would like to mention is that the EM algorithm that we derived here is also known as the soft k-mean algorithm, really. So it's called the soft k-mean, and of course there's an original k-mean algorithm. And the original k-mean algorithm is basically very similar to this EM algorithm here, but in the E step, instead of trying to find for each data point whether it belongs, the fraction belong to a particular membership, a particular cluster. For example, for a point here, maybe we'll say is 30% red and maybe 60% green and 10% blue, for example. Instead of like assigning like a fraction to each of the distribution, for each of the data point, it will only assign to a particular distribution. It will either say it should be red or green or blue. So and so instead of like having a soft decision here, we will have a hard decision for each of the data points. And afterward, the M step essentially is the same as this here, is trying to find the empirical mean and covariance. And actually this K-mean algorithm is also known as the Loimas algorithm, which is independently discovered among the source coding community. So that's really all for me. What I want to talk about this example of using EM algorithm for solving a parameter estimation of a Gaussian mixture model. And thank you for watching.